So this is a worksheet for section 11.2 dealing with vectors. We just want to do some basic operations with vectors here. Problem 1, we want to consider the vectors A, which is 3, negative 2, 4, B, which is 5, 0, negative 4, and the vector C is negative 2, 8, 3. We want to find the following vectors. So first thing we do is A plus B. We're just going to copy down A and B. So we have, let's see, 3, comma, negative 2, comma, 4. Whoops, wrong bracket. If it matters too much. Plus B is 5, 0, negative 4. And now when you add vectors, what you do is you add these component-wise. So what that means is you take the 3 plus the 5, and that's your new first component. For the second component, or y component, you take the negative 2 plus the 0. And then your third component, you're going to take the 4 plus the negative 4. And that gives you a vector, let's see, 3 plus 5 is 8. Negative 2 plus 0 is negative 2. 4 plus negative 4 is 0. And there's your answer. When you take A plus B, you get 8, negative 2, 0. Okay, next, we have A minus B. I'm going to scroll back up to remember what A and B are. So this is going to be 3, negative 2, 4, minus 5, 0, negative 4. Just like addition, subtraction is component-wise, but we subtract instead of add. So we get a new vector, 3 minus 5. Then we get the negative 2 minus 0. And then the third component is our 4 minus the negative 4. Okay, and then we want to do the arithmetic. 3 minus 5 is negative 2. Negative 2 minus 0 is also negative 2. 4 minus negative 4, that's 4 plus 4. That would give us 8. So A minus B is negative 2, comma, negative 2, comma, 8. Another one, we're going to do 3A minus 2B plus 5C. Scroll down a bit. So this is going to be 3 times A is the vector 3, negative 2, 4. Minus 2 times B, that's the vector 5, 0, negative 4, plus 5 times C, I have to look back up and see what the vector C was, negative 2, 8, 3. So C was negative 2, 8, 3. So I just sub in for A, B, and C. Now, when you have this coefficient out in front, this 3, that multiplies through by each of the elements of the vector, each component of the vector. So what I get here, this is 3 times 3, that's 9. 3 times negative 2 is negative 6. 3 times 4 is 12. So it scales that vector, basically makes it 3 times as long, but in the same direction. Minus, now I could write this as plus, and then do a negative 2 times 5. So it's negative 10. Negative 2 times 0 is 0. Negative 2 times negative 4 is positive 8. Plus 5 times negative 2 is negative 10. 5 times 8 is 40. 5 times 3 is 15. And then, as before, I add the components. So I get 9 plus negative 10 plus negative 10. That's 9 minus 10 minus 10. And then I get negative 6 plus 0 plus 40. And then I get 12 plus 8 plus 15. And so in the end I get, let's see, that's negative 20 plus 9, that's negative 11. 40 minus 6 is 34. 12 plus 8 is 20, plus 15 is 35. So it turns out that 3A minus 2B plus 5C is negative 11, comma 34, comma 35. So this is actually a linear combination of A, B, C, if you're familiar with that notation, or that terminology. Okay, another one here. We've got this symbol here. Now the vertical bars, it looks like absolute value. That's really magnitude here. So we're going to do the magnitude of the vector A, 3, negative 2, 4, times the vector B, b was 5, 0, negative 4. Now, what's going to happen here is the magnitude, that's going to give us a scalar that's a constant. It's going to be like, well, I guess the negative 2 here that we have here, and it's just going to multiply through by each of these components. So the magnitude, what we're going to get here is the square root of 3 squared plus negative 2 squared plus 4 squared. That's the magnitude of 3, negative 2, 4. We multiply that by 5, 0, negative 4. So that gives us, let's see, 9 plus 4 is 13, plus 16, that's 29. So I get square root 29 times the vector 5, 0, negative 4. And so our answer works out to be the vector 5 times the square root 29. And I sort of distribute this square root 29 to each component. I get a 0, and then I get a negative 4 square root 29. So there's our answer for magnitude of A times B. And then a similar thing, we just switch the A and B around. So I get magnitude of B times A. So this is going to be the magnitude of 5, 0, negative 4. Again, that's going to give us a scalar that's going to work down to be some number multiplied by the vector A, which is 3, negative 2, 4. The magnitude of B times A. And what we're going to get here, this time, so I'm writing the square root up here this time. So you get a square root of 5 squared plus 0 squared plus negative 4 squared, extend the square root a bit, times the vector 3, negative 2, 4. That works out to be, let's say we have 25 plus a 16. That's square root of 41 times the vector 3, negative 2, 4. And so that works out to be, now distribute the square root 41. So it's 3 square root 41 minus 2 square root 41. And then we get 4 square root of 41. Just kind of box up that answer there. Okay, so that's the first one, just doing some basic vector operations with some vectors chosen more or less at random. Here's another operation we can do. It's a vector. Generally, we can use this to describe sort of the magnitude and distance or the direction from one point to another. So the idea here is somewhere up in three-dimensional space there's a point, in this case 3, 0, 4, and then there's another point somewhere else. Note, I'm not really paying any attention to sort of where these points are in space or anything. I'm just drawing 2 points and then saying this one's 3, 0, 4, this one's negative 2, 5, 3. And the vector is going to go from here to there. So there's our vector. Now, to find that vector, what we get is it's going to turn out that the vector, we're going to take our end components minus the start components. So what we're going to get for our vector answer is we're going to take the x's. We're going to take a negative 2 minus, whoops, not comma, but minus the 3. So negative 2 minus 3. The y components is 5 minus 0. And our third component is 3 minus 4. So I just take end point minus start point, and I do that component-wise. And so the vector, what I get in the end here, see this is negative 5, comma, 5 minus 0 is 5, 3 minus 4 is negative 1. So it's the vector that goes from 3, 0, 4 to negative 2, 5, 3. Note if you took this vector negative 5, 5, negative 1, and added that to 3, 0, 4, you'd end up at negative 2, 5, 3. Okay. Here's another common thing where we have a given vector, and we want to find a unit vector in the same direction. So the general idea to create a unit vector is if I have some vector v as my general vector, then what I can do is u, this is a unit vector in that direction, it's generally going to be v divided by the magnitude of v. So if I multiply by a scalar here, by some constant of the vector, it doesn't change the direction of the vector. All it's going to do is scale this, and then if I take the magnitude of this new vector, I'll get magnitude v over magnitude v. I'll get 1. Magnitude 1, that's what makes something a unit vector. So in our case here, that was the general idea. Our case is going to be u. Now, this 5i minus 3j plus 4k, I can write that as a vector as 5, comma, negative 3, comma 4. I can use a component notation here. It looks a little bit different. Sometimes it's a little bit cleaner. Use either one. They're completely equivalent, just different bookkeeping. So what I get then is my unit vector should be 5, negative 3, 4, divided by the magnitude of 5, negative 3, 4. So I get 5, negative 3, 4, divided by the magnitude is the square root of 5 squared, plus negative 3 squared, plus 4 squared. So that gives me 5, negative 3, 4. So we get a 25 plus a 9 is 34, plus a 16, that gives us a square root of 50. Now, square root of 50 is going to be square root of 25 times 2. That's 5 square roots of 2. So I get 5, negative 3, 4, divided by 5 square root of 2. And now you can really divide component-wise or multiply by 1 over 5 square root of 2. So this is going to give me 1 over square root 2. Let's see, negative 3 over 5 square root 2, and you'll get 4 over 5 square root 2. And that's generally a completely sort of sufficient answer here. I'll box that up. Sometimes you'll see people go and rationalize the denominator here, and so you might see people multiply this by square root 2 over square root 2. When you do that, what you're going to get is new vector, square root 2 over square root 2 times square root 2 is 2. So rationalize the denominator means there's a 2 down there. There's no more square root. Right, so there's no more square root. That's what rationalizing means. And then I'll get a negative 3 over 3 times square root 2. And then I'll get 5. Square root 2 times square root 2 is 2. 5 times 2, that gives me 10. 4 square root 2. 5 square root 2 times square root of 2, that's 5 times 2, that's 10. Note this last component simplifies. So I get square root 2 over 2, comma, negative 3 square root 2 over 10, and 4/10 is 2/5, so that's the same thing as 2 square root 2 over 5. So sometimes you'll see this answer in red if you really want to rationalize the denominator. Generally the thing in green is, good enough for most purposes. It kind of depends what you're going to do with this or what other things you're going to mix that with later. Okay, last question. So now we want to find a vector of magnitude 12 in the first quadrant of the xy plane that makes an angle of pi over 6. There's a random s there that we don't need. Angle of pi over 6 with the x-axis. So what we've got going on here is here's our x-axis. And we say in the xy plane, maybe that's just a 2-coordinate vector. I mean, I could think of it as in the xy plane. Maybe there's a z coming out of this. We can make that component of the vector 0. I'm just going to do 2 components here. And what I want here is I want to get a vector out here where this length is 12 and then this angle is pi over 6. So what I'm going to do, first of all, is that if I'm going to do magnitude 12, and then I'm going to multiply by a unit vector with this angle being pi over 6, and that's going to be cosine pi over 6, comma, sine pi over 6. So I get 12 times cosine pi over 6 is square root 3 over 2. Sine pi over 6 is 1/2. And you distribute the 12. 12 divided by 2 is going to be 6, so you'll get 6 square root of 3, comma, 6. So this should be your answer here. So that should give you a vector in the correct direction, and hopefully it also has magnitude 12. We can check that real quick by doing a square root of 6 square root of 3 squared plus 6 squared. So that's a square root of, let's see, this is going to be 36 times 3, that's 108, plus 36. That's square root of 144, which is indeed the 12 we were looking for. So if you weren't confident that this had magnitude 12, you can do a quick check, and that works out. Again, I was saying earlier, if you want to think about this in three-dimensional space, so your answer in R3, let's delete R there. So let's do R3. Your answer, what you would do here, ugly arrow. Let's do a colon. You get a vector. You're going to get the 6 square root of, whoops, I'm in trouble here. So you get the 6 square root of 3 as the x component, 6 as the y, and then the 0 as the z. So you could write an answer like that if you're thinking of this in three-dimensional space. You know, it says xy plane, you're somehow we're thinking about it in z. Generally, if there's no mention of z, I might assume that we're just talking about in the plane in two-dimensional space. But either way works. And there we go for our worksheet, or at least our first worksheet on 11.2, just dealing with the vectors.